Hi, in this session we are going to study chapter 14, which is about interference of light. In this chapter and in studying interference of light, there is an important physical quantity which is called the optical path of light should be non-well. So, geometrical and optical paths of light. What is the difference between these two paths of light? Consider a medium, any medium of index n. So you have here medium of index n. Suppose you have a ray of light that covers distance AB in this medium, where the speed of light is v less than c. This distance covered by light in the medium is called the geometrical path. So AB is the geometrical path of light. Of course, this geometrical path is covered during time t. Now, what is the distance that corresponds to AB in vacuum? So this is vacuum. And as you know, light will cover a greater distance in vacuum during this time t, because its speed is c greater than v. So during the same time t, light in vacuum will cover distance a prime b prime, which is greater than AB. This distance, A prime, B prime, which is covered during same time t, is called the optical path of light. Okay, so A prime, B prime is the optical path of light. So let me put a definition for the optical path. The optical path of light is the distance covered by light in vacuum that corresponds to the distance covered by light in the medium during same time t. اوكي؟ يعني بالميديوم of index n, this is vacuum. In medium of index n, we said it covers distance AB during t. At the same time t, in vacuum, it covers distance A prime, B prime during same time t. Okay? يعني, what does this mean? This means I can change the medium to vacuum by placing distance AB by distance A prime, B prime. And if I do this, nothing changes in the problem. Okay? Now, relation between geometrical path and optical paths. There is a relation. Okay. How to find this relation? If you look here, you know that the distance covered by the wave is equal Vt. Now, in the medium, distance covered is AB during time t. So I replace x by AB, and the speed is considered to be v times t. I am going to call this equation 1. In vacuum, also, I am going to apply this in vacuum. Distance is A prime, B prime, but the speed here is c. So, A prime, replace x by A prime, B prime, the speed is c during same time t. This is equation 2. How to find relation between A prime, B prime, and AB? I am going to divide 2 by 1, okay? 2 divided by 1, this implies A prime B prime over AB is equal CT over VT. T cancels with T. You get A prime B prime over AB equals C over V. But what is C over V? It is the index of refraction of the medium. So I can write it is equal to n. Yani this implies A prime B prime is equal NAB. Okay? So this is the relation between optical path and geometrical path. Yani, for example, let's take an example here. Example, suppose you have a glass. As you know, the index of the glass is 1.5. If I have light passing through glass and covers, for example, 10 meter, AB is equal 10 meter. This is the real distance covered by light in a glass. This is the geometrical path of light. Okay? Type. So the optical path A prime B prime of light is 1.5 times 10 gives you 15 meter. يعني, what I have done here, what I can do, I can remove the glass and replace the glass by vacuum on condition that I consider light has covered 15 meter. Okay? This is called the optical path. And it is very important, the quantity and interference, the optical path. Look here, for vacuum, you know that for vacuum N1, يعني this implies A prime B prime equal AB. يعني in vacuum, if light covers, for example, distance 10 meter, I am working in vacuum, it covers 10 meter. This is the geometrical path, 10 meter, real distance covered by light. If I ask you what is the optical path, you are going to change this medium, which is vacuum, to vacuum in order to find the optical path, and you write A prime B prime equal NB, but N1, so you get A prime B prime equal AB. What? يعني, this means that in vacuum, the geometrical path of light is also considered to be the optical path of light. Okay? They are the same in vacuum. For air, you have N approximately equal to 1. Replace, this means A prime, B prime will be equal approximately AB. So if I am working in air and all the experiments are in air, and I consider certain distance covered by light in air, for example 10 meter, the geometrical path is 10 meter and the optical path is also 10 meter, because if the geometrical path is 10 meter, what is the optical path? I should change this air to vacuum. But I am going to replace the distance covered by light in air to that distance covered by light in vacuum. So I replace N1, I get approximately the same distance. So I can consider the optical path of light in air and the geometrical path of light in air can be considered the same. Okay, keeping in mind the importance of the optical path, and you should understand it well, I am going to study the interference of light experimentally. Okay? So let us see Young's experiment for double slit here. And this is experimental study, as I did previously in all cases. Every time I make experimental study and then theoretical study. So let's see the experimental study of interference of light, which is called Young's double slit experiment. Okay, Young's double slit experiment. Young did this experiment in 1801. And it is the real experiment that proved light has wave properties. Okay? What does he did, Young? He took a cardboard here and made a thin slit, okay, less than 1 millimeter, which is very small slit. And he took also a cardboard and made 2 slits within it, separated also 2 thin slits, also in the order of 1 millimeter and less. Okay, 2 slits. And here, this is the observation screen in order to see what will happen on the screen. He sent a beam of light towards the first slit. Because this slit is very small, less than 1 millimeter, it diffracts, okay? Diffracts, notice. Here, this is a cylindrical beam. Because light is diffracted, it becomes divergent beam, okay? Bending of light took place at the edges of the slit, like this, okay? This divergent beam reaches the 2 slits. Also here, the slits are very small. Also, light diffracted at this slit and at the second slit also. So, you get a divergent beam. Also here, you get a divergent beam. As you see, these 2 beams superpose. There is a common region here where the 2 beams superpose. In this common region, on the screen of this common region, he noticed like this pattern, okay, which is called the interference pattern of light. This is what we have single slit pattern. You obtain a single slit diffraction pattern. Yani when you have 1 slit, as we did in the previous lesson, you have obtained a large central bright fringe which has double the widths of the lateral fringes. But here in double slit pattern, in Young's double slit experiment, notice here, okay, you have a bright fringe, dark fringe, bright, dark, bright, dark, bright, dark, and so on till at the end, okay? So there is a difference in the superposition of the waves coming from 1 slit or from 2 slits. This figure is schematic drawing, not a real one, but schematic drawing in order to see. Here, the slit has larger lengths from this case, okay? Because of this, the dark fringes are longer than these, as you see here. This is the dark fringe, the green are the bright. Dark, bright, dark, bright, okay? So, and that's what I want to say only. So, if I ask you to describe the diffraction, the interference pattern that is seen on the screen, what do you say? You say that the interference pattern consists of alternating bright, dark, alternating dark and bright fringes that are equidistant from each other. Yani, distance from here to here is the same as the distance from here to here, the same. They are equidistant from each other. And as you know, they are rectilinear rectilinear, can be considered rectilinear and not like the diffraction pattern. Okay? That's what I am to say only, and I will draw all this on the board and continue. So Young's double slit experiment. Young's double slit experiment. Experimental study. Experimental So, here you have two small slits on the screen. This is a screen. I am going to name these slits S1 and S2. And here this distance, which looks very large, it is also small distance, less than 1 millimeter, okay? I can send a laser beam. This is the laser beam, which is a cylindrical beam towards S1 and S2. And I want to observe what happens at a screen E placed at distance D from the plane of the slits, okay, which about 1 meter or more. So as we said here, light will diffract by S1 and S2. To make a good figure, take the midpoint of segment S1, S2. I am going to call it I. The orthogonal projection of I on the screen, I am going to call it O. This is O, okay? Now, we said here, because S1 is less than 1 millimeter small, it diffracts. So this is the first diffracted beam of light, okay? Now, also at S2 there will be diffraction, okay? If S1 had the same size as S2, the same diffraction that happens at S1 will happen at S2, and you will get here a ray parallel to this one. I'm going to put here two arrows to distinguish this one from this one, and the beam coming from S2 from the beam coming from S1. And you get the second ray here, diffracted ray, parallel to this one, okay? So, as you see, these two diffracted beams superpose in this region, okay? This is the zone. This zone is called the zone of interference, okay? The zone of interference. This is called the zone of interference, zone of interference, okay? Where the two waves superpose together is called the zone of interference, okay? If I call this X, point X, capital X, and this one point capital Y, X or Y XOY is the zone of interference on the screen. We will prove later that at O there will be central bright fringe, sol O, which is the midpoint of XY, the position of the central bright fringe, a bright fringe. Okay. On this zone XOY, and due to the superposition of waves from S1 and S2, what do we observe? We observe an interference pattern, okay? So, on the screen, in the zone of interference, we observe bright and dark spots that are called the fringes, and as you see, they have the following shape, okay? You get, this is bright, this is bright fringe, as you see in the figure on the board. This is the bright fringe. And then this is the dark one. This is the dark, bright, dark, bright, and so on, okay? Let's describe this, okay? So, interference fringes, what do they have properties or characteristics? The interference fringes are alternating. Alternating means one bright, one dark, one bright, one dark. It is impossible to obtain two successive brights or two successive dark. Alternating. As you see, they are rectilinear. Okay, equidistant. Distance from the center to the center here is the same as the distance from here to here. We say equidistant. Dark and bright fringes parallel to the slits. These are the two slits, and the fringes are parallel to the slits, parallel to the slits. So you have one property. This is the first one, rectilinear the second, equidistant third, dark and bright fourth, and parallel to the slit 5. And as you see, the description of the interference fringes differ from that of the diffraction pattern. Okay? Now, I want to interpret the presence of dark and bright fringes. Why there is dark and bright fringes? Let's see. This is screen E. This is O. This is E. This is X, O, Y, the zone of interference on the screen. Okay? And here, this is the plane of the slits. S1, S2, and this is the midpoint I, and there O is the perpendicular the projection of I, okay? Where I is the midpoint, and here this is the laser beam. So, interpretation here, I am going to choose a point P within the zone of interference. This is P. Yani a point here, for example, P. This point P receives two waves, one coming from S1 and another one coming from S2, okay? This one covers distance D1 and the second covers distance D2, with D2 greater than D1. So there is a difference in this distance. There is a difference, okay? This difference, I am going to call it geometrical path difference, which is the same as the optical path difference. Okay? فإذن the presence of bright fringes now you have two light waves reaching a point M. And as we said, a light wave is an oscillating electric and magnetic field. I'm going to take the electric field because the intensity of light depends on the amplitude of the electric field. This is one wave coming from S1. Okay? Here, this is E1, the maximum value of first electric field. And this is the second one coming from S2. This is E2. If these two waves reaches point B in phase, يعني maximum with the maximum, what happens to the electric field? The electric field will be additive. يعني this is point P, this is point P. They reach, this is E1, and this is what? E2. So the amplitude of the electric field will be their sum. Okay, يعني you get a resultant field E1 plus E2, and E1 is equal to E2. So you get a maximum amplitude of 2E. This happens at the center of the bright fringe. And so the center of the bright fringe will have the higher intensity. And this is why we obtain a bright fringe. Okay? So, bright fringes are formed. Bright fringes are formed when light waves leaving S1 and S2 reach the center of the bright fringes in phase, okay? Time. What is the condition to reach in phase? Okay, فإذا here الcondition for the waves to reach in phase at the center of bright fringes. Okay, time. Let's see. If this is source S, laser beam here, this is the source S, the main source of laser beam. As you see, for light to reach point P, it follows two passes. The first one S1P, okay, which is what? Which is SS1 plus S1P. Because we are working in air, I can consider the geometrical path the same as the optical path. Okay, don't forget this. So I can write here equal to the optical path. Also another path, geometrical path, the first geometrical, second geometrical path, which is equal S2P, which is equal SS2 plus S2P, which is also the second optical path, the same, because in air, optical path. If I say optical path differences, this means that I want to subtract them. So, the optical path difference, I'm going to represent it optical path difference here, or geometrical path difference in this case, because they are the same. Okay? What is it? I'm going to call it delta. Delta difference. So let us subtract this. S2P minus SS1P, you get S2 plus S2P minus SS1 plus S1P. Look here, SS2 is equal to SS1, okay? This is a rectangle. So I can cancel this with this. you get here S2P minus S1P. So the optical path difference is S2P or D2 minus S1P or D1. How to indicate delta on the figure? If I drop from S1 a perpendicular to S2P, this will be the optical path difference from here to here. This is delta, or geometrical path difference, which is the difference of D2 minus D1. Now, if this delta, the optical path difference, is a whole multiple of the wavelengths of light, center of bright fringes, this optical path difference must be equal, delta equal k lambda, okay? Whole multiple of lambda, where k here is equal 0, plus minus 1, plus minus 2, plus minus 3, etc. K is called, is the order of the bright fringe, okay? Now, when S1P minus 1 S2P minus this one is equal 2 lambda, 1 lambda, 2 lambda, or 0, or 3 lambda, or minus 3, then these rays meet at the center of the bright fringes, okay? Now, what about dark fringes? The dark fringes, dark centers of dark fringes, since I am talking about the centers, okay? Also here, look here, suppose this is P and these are the rays coming. Suppose from one source S1 the ray reaches P like this. This is E1, okay? From S2 the ray reaches B in this form, opposite to it, yani like this. This is E1. This is E1. So what will happen here? As you see, the wave will cancel each other. Okay, yani you will get E equal E1 minus E1 gives you 0. So you get a dark fringe. Here the dark fringe doesn't mean there isn't light, because dark means no light. Dark fringes here, these dark spots, lights reach them, but this light cancel each other, and so you get the dark fringe. Okay, فإذن waves leaving S1 and S2 reach the centers of dark fringe in opposite phase. opposite phase. Opposite phase means like this. One is maximum, the second is minimum. So they cancel each other. Now, what is the condition here? Condition to obtain the center of the dark fringe. This delta, phase difference delta, must be equal odd number of half wavelengths. Okay? Also here, k prime equals 0 plus minus 1 plus minus 2. Well, k prime is the order of dark fringe. Okay? يعني if k minus 1, this is the first dark fringe. K minus 2, the second dark fringe, and so on. This is what we mean by order. The same for the bright fringes. Last note about the optical path difference. We said here delta equal S2P minus S1P. If S2P equals S1P, what does this mean? This means that we are at the center at O, because at O you have here, this is S1, this is S2. At O, these are equal. So this means that the point of the point is at O. Type. Look here, if S2P greater than S1P, where will be the point? This is equal to this. For S2P to be greater than S1P, this means that P should be above O, so that the distance S2P is greater than S1P. So in this case, I write the point is towards the side of S1. Why I am saying toward the side of S1 and not above O? Suppose S1 is below and S2 is above. P will be below. Yani always P is toward the side of S1. Also, if the last case, if S2P smaller than S1P, yani this is P, S2P smaller, for this to be greater should be greater than S1O, yani this means it will be below O, and this is P will be. So I say that P, the point, is on the side of S2, and this is the end of the experimental study. Now I am going to talk about theoretical study